I guess we better do something.
So this is February 3rd. Let's look at our schedule for a minute. See where we're supposed to be. So we're a little behind schedule. We're supposed to finish chapter 2 last week, but we still need to finish that and then move on to chapter 3. Exam scheduled for next week sometime. I don't have the day on there, Monday, Wednesday, or Friday. We can decide that with your input. Doesn't matter to me really which day we do that. But might as well assign the first homework assignment. And that's on Moodle under this week, lecture February 3 to 7. Down here it says homework assignment, passenger pigeon. So that'll be due a week from today, Monday. Let's open that and look at it. So just read this article. It's a few pages long, but it'll take you 15 minutes or something to read it. You guys know the story of the passenger pigeon? Ever seen one, passenger pigeon? I haven't, because they went extinct over 100 years ago, so you probably won't see any. If you do, take a picture, because it would be important news to find one of them alive. This is a very important story, a very sad story. It's hard to believe what happened to that. Here's a picture. It's not showing up. There's a picture of it. It's a very pretty bird, but at the time that the Europeans first came to North America, it was the most abundant species of bird in North America, probably in the world, maybe the most abundant species of bird that ever lived. There were probably more passenger pigeons in North America than all other species put together. And now they're extinct because humans managed to kill off every one of them. So it's very, very sad story. So you just need to read that and then just answer these few questions. And they're just questions about facts that are in the story. Except the last couple I think are more opinion. So no right or wrong answer to those. But please don't just read the questions and look through and try to find the answers. Actually read it. You'll probably get done faster if you read the story and then answer the questions, rather than try to skip reading it and just look up the answers. Okay, so due next Monday. I'll if I remember, I'll remind you again on Wednesday and Friday about this. Okay, so we need to go back into chapter 2. Finish this chemistry business. So we went over this stuff about chemical bonds, the ionic and covalent bonds, and the octet rule. Remember, the first electron shell can hold 2 electrons, second can hold 8, third can hold 8. Beyond that, we don't care, because in biology, the elements whose atoms have lots and lots of electrons are the ones that do not occur in living organisms. So we're not so concerned with them. We're talking about covalent and polar and non-polar covalent bonds, and hydrogen bonds, the weak attractions between water molecules and liquid water. Surface tension, heat capacity. Where did we stop? Anybody remember?
I think we just looked for the picture of the man on water.
Oh, okay. Okay. So we talked about surface tension, right? Surface tension, it's like a skin on the surface of liquid water caused by the hydrogen bonds among the water molecules because they are polar. So the negative end of one polar molecule is attracted to the positive end of another. And so that causes the surface tension in water, also causes some other properties that water has that are kind of unusual. We say water has a high heat capacity. That means it takes a lot of energy to heat water, to raise the temperature of water, compared to many other liquids. Because water molecules are polar, and there are hydrogen bonds between water molecules. So if you would put a, what happened now? Lost the image. There's P. Okay. If you would take a pot, he had a stove with two burners, and you turn them both on high, so they're both putting out the same amount of heat. And you put a pot of water on one and a pot of something nonpolar like gasoline on the other, which that would be a very bad idea to put gasoline on the stove. But so the gasoline would heat up much faster than the water. The temperature of the gasoline would rise faster than that of the water, because heat. You need to know what heat is, what heat energy is. In liquid water or a gas like air, the atoms and molecules are always moving around and bouncing off of each other. That's heat energy. So the faster they're moving, the more heat energy there is, and the higher the temperature. So if you're trying to heat water, the heat is making the molecules move faster, but at the same time, there's hydrogen bonds pulling the molecules toward each other, and so it's resisting that movement. So it takes more. You have to add more energy to get water molecules moving than to get gasoline molecules moving, because gasoline molecules are nonpolar. There's no hydrogen bonds between them. And that's important in biology, heat capacity of water. But for one thing, there's a lot of water in the environment. Water in the soil, water vapor in the air around us. And so during the day, when the sun's out and the environment is receiving a lot of energy from the sun, it heats up that water and in the soil and air, so that water is absorbing a lot of heat energy. And then at night, the sun goes down. We're not receiving heat, we're not receiving energy from the sun, but the temperature in the environment stays fairly warm because of all that heat that the water in the environment has absorbed during the day. So that's why, especially in geographic locations that are near a lot of water, or near an ocean or a big lake, the the temperature does not fluctuate as much between the daytime and nighttime. Um, but in a desert, why do deserts get so hot? It's mainly because there's not much water in the environment to absorb the heat um, during the day. And then at night, you ever visit a desert, like go to the Arizona desert, and camp overnight, or just live someplace like Phoenix. Um, Very blazing hot during the day, but as soon as sun goes down, the temperature can drop 40 degrees, and it's because there's um, not much water in the environment to absorb the heat during the day, and then prevent the temperature dropping at night. So it's important. High heat capacity water is important in environmental biology. Um, Evaporation. It takes a lot of energy for water to evaporate, and that's important because of evaporative cooling is one way that we regulate our body temperatures. Your body temperature starts to get too high, you start to sweat more, and that water, when it reaches the surface of your skin, it evaporates. And it takes a lot of energy to evaporate water. So every molecule of water that goes from liquid to vapor, it takes a lot of energy with it. And so that's why when you're wet, you feel cold because of that evaporation. Um, uh, because of um, hydrogen bonds between water molecules, that makes liquid water pretty dense. It's heavy. It's heavier than oil because the molecules are closer together because of the hydrogen bonds pulling them together. And that's why if you try to mix oil and water, the water sinks to the bottom and the oil floats. The oil is less dense. Um, and the fact that ice floats on water that's an unusual property of water. In most other substances that occur as liquids and solids, the solid is heavier or more dense than the liquid. Um, so if we had some a metal like lead melts at a pretty low temperature. If we have a tin can and put lead in it and put it on the stove, the lead would melt. But then so now we have liquid lead. If we would take a chunk of solid lead and put it in there, it would sink to the bottom. Whereas in water, the solid form, ice, floats on the liquid. And that's important in the environment because as a lake freezes, it freezes on top first because the ice floats. If the ice would sink, then lakes would freeze from the bottom up. And when a lake starts to freeze on top, that layer of ice acts as insulation between the water and the colder air in the winter, and so it slows down the freezing. And so lakes hardly ever freeze all the way to the bottom. And if they did, then all those fishes and other animals in the lake would not survive that. Okay, so some terms here we need to know: solution, solute, and solvent. A solution is just something dissolved in a liquid, and the liquid we call the solvent. So that could be water or oil or alcohol. And a solute is what's dissolved in the liquid. So sugar water would be a solution. Water would be a solvent, sugar would be the solute. And of course there can be more than one solute in the solvent. These terms hydrophilic and hydrophobic. Hydrophilic means that something likes to dissolve in water. So that would be other polar molecules, like sugar is a polar molecule, so it's hydrophilic. It dissolves in water just fine. Hydrophobic means it doesn't like to dissolve in water. So non-polar stuff like oil, gasoline, are hydrophobic. Um, okay, this shows I mentioned before when we talked about ionic bonds that molecules that are held together by ionic bonds, if you put them in water, the ions separate. The ionic bonds come apart. And in liquid water, we see that the ions, for example, sodium chloride held together by ionic bonds, separates in the chlorine and sodium ions. But because these water molecules in liquid water are polar, the negative end of the negative end of oxygen molecules are attracted to the positive ends of the sodium, and the positive ends of the water molecules are attracted to the negative chlorine ions. And so those sodium and chlorine ions mix very well in water. So ions are hydrophilic. Okay, pH and bases, pH and acids and bases. So, let's consider a container of liquid water. So these are water molecules, H2O, and so these water molecules in liquid water are always moving around, bouncing off of each other, and sometimes when the two of them come together, one of them will break apart. And when that happens, it forms these two ions, an H plus, so hydrogen, positive hydrogen ion, and this one called it's OH minus. It's called hydroxide. But so there's one of the hydrogens, there's the other, and there's the oxygen. So these will maybe eventually come back together, or this H plus will come back, will join with this OH minus and form a water molecule again. But this happens all the time in liquid water. So at any given moment, some of these water molecules are broken apart into H plus and OH minus, and there would always be the same number of H plus as OH minus in pure water, because you get one of each from each water molecule that's broken apart. In pure water, where the number of H plus equals the number of OH minus, we say that is neither, pure water is neither acidic nor basic. An acidic solution is one in which there's more H plus than OH minus. A basic solution is one in which there's fewer H plus than OH minus. And so if we would do something that would add more H plus to this water, we would make it basic. And what could we, what we could add is an acid. So this is nitric acid, HNO3. It's held together by ionic bonds, and so when you put it in water, it comes apart into these ions. I'm sorry, this got cut off. It should be NO4 minus or something. But this is the important part. You put this nitric acid in pure water, it will be adding H plus to it, so making it acidic. If you add something like sodium hydroxide, this is Ly, Lye. This is a base. If you add this to water, it also comes apart into these ions. But there's that OH minus. It's adding OH minus, and now there's fewer H plus than OH minus. So now this is a basic solution. I'm gonna back up, go back to this slide. And pH is a measure. It's a number that is a measure of how acidic or how basic a solution is. And that number goes from 0 to 14. Right in the middle of that range is 7, which is neither basic nor acidic. So we say it's pH neutral. Equal number of H plus and OH minus. But if the pH is less than 7, that means the solution is acidic and has more H plus than OH minus. So if the pH number is more than 7, then it's a basic solution. Fewer H plus than OH minus. So this pH is a measure of how much H plus is in a solution. And it seems backwards that the more H plus there is, the lower the pH number is. It's just because of the weird formula that is used for calculating the pH. You don't need to know that formula, but what you need to know is that low pH means high H plus, which means acidic, and high H plus means low H plus. High pH means low H plus, which means basic. Here's some familiar solutions that are acidic and basic. So right here in the middle, pure water, distilled water, nothing in it except H2O. Equal amounts of H plus and OH minus. So the lower this number, the more acidic it is. So you say the stronger an acid it is. So urine is a little bit acidic. Coffee, tomato juice, orange juice. So you have citric acid in them. Tomato juice, orange juice. Lemon juice is pretty acidic. Gastric acid. What does gastric mean? Stomach. So that's we have hydrochloric acid in our stomach, and it's a very strong acid. If we didn't have a very thick layer of mucus in the lining of our stomach, that acid would burn your stomach tissues. Above 7, these are all basic. So seawater is a little bit basic. Baking soda is a base. Milk and magnesium, ammonia, soapy water, bleach. My dad, when I was a kid, he used to mix baking soda in water if he had an upset stomach, and he'd drink that. The idea was if his upset stomach was from acid in his stomach, irritating his stomach, then that baking soda would neutralize some of that acid. If you mix a base and an acid together, then you would get a solution with a pH somewhere in between. This is stomach acid is 1. If we would mix some baking soda with that, it would make that less acidic. Milk and magnesium, it's the same reason people take that for upset stomach. It's a base, it neutralizes stomach acid. Something these bases, especially strong bases, have in common is they feel slimy and soapy. You get any of these, just put baking soda in water, it feels soapy. Ammonia, soapy water, bleach, you get any of those on your hands, it feels soapy and slimy and kind of hard to rinse off. Acidic solutions don't feel soapy and slimy. Okay, buffers. A buffer is something that if a solution has a good buffer in it, then the buffer stabilizes the pH. So that means if you add some acid to a solution with a good buffer in it, then the pH of that solution will not change very much. Or if you add some base to it, the pH of the solution will not change very much. It stays the same because the buffer, like if you add H plus to a solution that has a buffer in it, the buffer soaks up the H plus. So it doesn't make the solution more acidic. And that's important in biology because, well, there are buffers in the environment, but there's also buffers in your body. The pH of your blood needs to be within this very narrow range. If it's just below that, then you are in a medical condition called acidosis. If it's above that, it's in alkalosis. The word alkaline means about the same as means the same thing as base. Not exactly the same, but just about. So an alkaline solution is a basic solution. So if you would, we see here that lemon juice is very acidic. If you drink 3 glasses of lemonade, is your the pH of your blood going to drop real low and you're going to go into acidosis? Why doesn't that happen? It's because you have good buffers in your blood. So if you drink a lot of lemonade, you're going to be adding more H plus. But you have this buffer system in your. This is one of. There's a few buffer systems, but this is the most important one in your blood. So you always have this H plus and these other ions called bicarbonate, HCO3 minus. You always have a lot of this in your blood. But if you add more H plus by drinking lemonade, those extra H plus will just combine with the bicarbonate ions that are in your blood, and it'll form this molecule of carbonic acid. And so it's taking the H plus out of your blood, and so it doesn't make your blood more acidic. This carbonic acid is also formed from the carbon dioxide that your cells are always producing. It's just a waste product. When the carbon dioxide produced by your cells goes into your blood and mixes with the water in your blood, it forms these carbonic acid molecules. So, but then when your blood gets to your lungs, where you can exhale the carbon dioxide, these molecules can come apart, and now you exhale this stuff. So these arrows, these chemical reaction arrows, have arrowheads on both ends because these reactions are always going in both ways, both directions. If you eat something that's very basic and you're adding OH minus to your blood, now you have less H plus than OH minus, but you've only got carbonic acid molecules in your blood that can come apart and add more H plus as needed. So this buffer system, these reactions are always going in both directions as needed to keep your pH where it needs to be. Now organic chemistry. So the word organic has a few different meanings. If you go to Walmart and the groceries, to the produce section, and they got bananas, and then they got organic bananas. That's not what this is about. Organic can mean natural. Like organic foods are the ones that are grown without chemical pesticides and artificial chemical fertilizers. They're grown naturally. The word organic can mean lifelike, but in chemistry, organic means carbon compounds. And this word organic comes from the early days of chemistry when chemists were discovering certain compounds that they only saw in living organisms. They never would see them in the environment by themselves. And they were proteins. carbohydrates, fats, and oils. And so they called them organic compounds. They thought that they could only exist in living organisms. They couldn't even figure out how to make those molecules in labs. But now, by now, chemists they know how to make thousands of organic compounds, and that the whole plastics industry is based on artificially produced organic compounds. But we still use this old word organic as if those compounds only exist in living organisms. So in order for a compound to be considered organic, it has to have at least one carbon atom in it and at least one hydrogen attached to a carbon. So the smallest, simplest organic compound is methane, CH4. It's one carbon. Glucose, C6H12O6, it has both carbon and hydrogen. Ethanol, carbon and hydrogen. Carbon dioxide, though, CO2, is not considered to be organic because it doesn't have the hydrogen. It's carbon and oxygen. There's many, an infinite number of possible organic compounds. Carbon, remember, has, let me find a picture of carbon. Yeah, carbon has 4 atoms, or 4 elements, or 4 electrons in its outer shell. It would like to have 8 to be stable, right? So it can form 4 covalent bonds around it. For example, methane is a carbon with 4 hydrogens. Each one is a covalent bond with the carbon sharing electrons, so that way the carbon gets 4 more electrons in its outer shell. So each carbon atom can be bonded to 4 other atoms, and that's one of the reasons that carbon is such a carbon that there are so many organic compounds because those. Well, here's that methane, carbon with 4 hydrogens, but these could be other. This could be oxygen and phosphorus and nitrogen, and many organic compounds have a long chains of carbon atoms like this with other stuff attached. This one's called a hydrocarbon. It has only carbon and hydrogen, and this one has 6 carbons. This one is called hexane. Hexane means 6, right? If it has 7 carbons, what would you call them? Heptane. Hept means 7 in Latin. What about 8? Octane. Ever heard of octane? When you buy gasoline, that says on the pump that number 87 or 89 octane. That's what it means. It's that number is the percent of the hydrocarbons in that gasoline that are octane. There are also in that gasoline not just one thing. So it's a combination of different lengths of hydrocarbons. There are some hexanes in there, some heptanes. Octanes are the best. They have the most energy. So if you use high octane gasoline, your engine could be a little more powerful, maybe get a little more gas mileage, but it costs more. There's glucose. It's in the form of a ring like this. It can also, glucose can also straighten out, be a straight molecule. It can be both ways. If you go to university and major in biology, you need to take a whole year of organic chemistry. So you need at least 1 year of general chemistry and then a whole year of organic chemistry. Organic chemistry is hard. It's Organic chemistry, probably the most common reason that people don't get into medical school. I've known a lot of people who went to college, majored in biology, planning to get into medical school and be a doctor, but they can't get through organic chemistry. Or one of my best friends, he got C's in organic chemistry. Took it twice. Got C's the second time. No way he's getting into he wanted to be a doctor, but no way he was getting into medical school. So became a high school biology teacher instead. That happens to a lot of people. Okay, lots and lots of organic compounds, but there are some types of these groups or types of organic compounds they're large and they make up much of our bodies and the bodies of other organisms. Carbohydrates, lipids, proteins, and nucleic acids. We call these biological macromolecules. Macro means large. And these are also what makes up most of the food that we eat, right? So what do we eat? We eat other organisms that are made up of the same types of molecules or similar molecules to what we're made out of. Most of these are polymers. Poly means many. So these are long chains of smaller molecules that are called monomers. And, we'll see what those polymers and monomers look like in a minute. So we need to look at each of these groups a little bit. So carbohydrates. So the nutrients used for energy in cells. So these are sugars, starch. These kinds of sugars are, especially glucose, is very easy for your cells to break down and get the energy out of them. So we eat nutrients, we eat food, your digestive system breaks them down into small enough molecules that they can be absorbed into your blood, and your blood delivers them to your cells, and your cells use those nutrients like sugars for energy and also for reusing the atoms and molecules in those nutrients for making, cells are always making new molecules. But your cells are really good at breaking down sugars to get the energy out of them. So breaking down these larger molecules into smaller ones, and it releases the energy that was in the bonds holding those atoms together. So this is short-term energy storage. So you eat, these starch and glycogen, short-term energy storage. Starch and glycogen are, let's talk about sugars first. So monosaccharides, disaccharides, and polysaccharides are the three types of carbohydrates. And they just differ by size. Mono means one. That's just one relatively small sugar molecule, like glucose, fructose, lactose. Glucose is what your blood sugar is. It's C6H12O6. I think we got a picture. Yeah. So here's two pictures of glucose. Remember I said it can be in a ring like this, but it can also straighten out. So this is what your blood sugar is. This one, fructose, that's fruit sugar. We all eat, most of us probably eat too much of that because that's in a lot of processed foods. Look on food labels and you see high fructose corn syrup everywhere. And then the lactose and other monosaccharides. These sugar molecules are small enough that if you eat them, they don't have to be digested any further. They're small enough that they can be absorbed right into your blood and go to your cells. Disaccharides, it's just two monosaccharides stuck together into a bigger molecule. Some double sugars. Of course, saccharides is just Latin for sugar. So this is a single sugar, double sugars, many sugars. So there's examples of double sugars: lactose, maltose, sucrose. Sucrose is it's just table sugar. It's called. You put on in your coffee or on cereal. Um, and that's just sucrose is one glucose and one fructose stuck together into one molecule. And this is too big to absorb into your blood. So when you eat this, it has to be digested. It has to be broken into the glucose and fructose, and then they can be absorbed into your blood. So we have chemicals, those enzymes in our small intestines that break the bond between the glucose and fructose. Notice these ended OSE, and OSE that see OSE on the end of the word, and chemistry probably is sugar. Lactose, what's that? Yeah, it's in milk. It's a dairy product. It's milk sugar. That's I think a glucose and a galactose stuck together. Lactose. Some people are lactose intolerant. That means they cannot digest this stuff. Just like sucrose, it's too big to absorb into your blood. It has to be broken apart into these two, which can be absorbed. But if you're lactose intolerant, you don't have the enzyme. Your intestines don't have the enzyme to break that bond, to digest it. So you can't absorb this in your body. So if you're lactose intolerant, you eat this, instead of this being broken apart and then absorbed into your blood in your small intestines, it continues all the way through your small intestines and goes into your large intestine. What do you have a lot of in your large intestine all the time? Bacteria. Living bacteria. They're supposed to be there. They're good bacteria. They're not harmful disease-causing bacteria. And so those bacteria do some good things for us. Some of them, they make some vitamins that we absorb into our blood and stuff. But the gas, the intestinal gas that is produced by our digestive systems, that's produced by those bacteria. If you didn't have those bacteria, you would never fart. So that's where that gas comes from. But those bacteria, they're not used to having sugar come into the large intestine, because normally the sugar is digested and absorbed before it gets there. But now, if you're lactose intolerant, you eat lactose, it goes in there. Those bacteria just have a big feast on that sugar, and so they produce it produces a lot of cramping and gas and diarrhea and unpleasant symptoms. Those people, they just don't have the enzyme to break that apart. We're unusual kind of in North America, in the United States, that most of us can digest lactose as adults, but in many parts of the world, almost all adults are lactose intolerant. They can only digest lactose when they're infants, little kids, but then they outgrow that and then they can't digest it anymore. Maltose, that's malt sugar. That's used in brewing beer and other alcoholic beverages. So I have a little beer making kit. I make beer sometimes, and so you have to you add yeast to this mix, and then you have to add maltose. That's the food for the yeast that ferment and make the alcohol and the carbonation, the carbon dioxide, the carbonate of beer. Okay, calling means many, so many monosaccharides in a long chain, so that would be a polymer, a long chain molecule made up of monomers, which are monosaccharides. Um, and so that includes starch and glycogen. These are both very similar molecules. They're both long chains of glucose. So starch is in plants. Glycogen is in animals like us. Starch is just a plant storing energy for later. Plants make glucose, sugar by photosynthesis. They often make more than they need right now. So the extra, they just link it together in long chains, and that's starch. And they store that in the plant somewhere, like a potato is just where that potato plant is storing energy underground for later. Um, Animals like us do the same thing. It's called glycogen. If you eat more glycogen than you need, your liver will take the extra, put it together in long chains, and store it in the liver. We also store glycogen in our muscles, skeletal muscles. Um, then when you don't eat for a while, you don't eat for several hours, now your blood sugar is dropping, your liver will break this apart into glucose and put it back into your blood, bring your blood sugar level up and provide energy for your cells. Um, um, so it says short-term energy storage. So this is just for we store glycogen usually just for hours, um, but for long-term energy storage, that's what the fat is for on our body. So if you eat so much, you got so much glucose in your body that your liver can't hold anymore glycogen. Then your liver can convert glucose into fat and then store that on our bodies, and that's how we gain weight. And that's more long-term energy storage. So if you don't eat for a while, your body will use up the glycogen. If you use up all the glycogen, then your body will start using the fat, your body fat, and that's how we lose weight. What happens if you think? What do you think if we use up all the fat on your body? It wouldn't take me very long. I wouldn't last very long if I was starving because I don't have much. But then your body starts using protein. Where do you have a lot of protein? Your muscle. So your body will start eating breaking down your own muscle tissue. Cellulose. This is plant fiber. We can eat starch and glycogen and digest it and use the glucose. But cellulose, this is also long chains of glucose. The difference here, they're all chains of glucose, just different kinds of bonds in between the glucoses. But cellulose, we cannot digest this stuff. We don't have the enzymes to break the bonds between the glucose and cellulose. So we're supposed to eat plant fiber, though. We're told it's healthy for our digestive systems, even though it just goes through you and comes out in food, because we can't digest it. So that's what wood is, mostly cellulose. And paper is made of wood. Other animals can digest it, like cows, cattle, mostly what they eat, cellulose. They can digest it. And termites, they eat wood. They can digest that stuff, but you can't. So here's polysaccharides, so starch, glycogen, cellulose. Chitin is another one with a C. This is what the exoskeleton of insects is made out of, and also the fungus cells have a cell wall around them. The cell wall in plant cells is made out of cellulose, but the cell walls of a fungus cell is made of this chitin. But they're all chains of glucose molecules. Okay, so we talked about carbohydrates, lipids. These are what they all have in common is they're nonpolar, hydrophobic, so they don't mix with water. So this is fats and oils. So long-term energy storage, like we said. Nutrients used for energy cells. So if you eat fats, your cells can use that, break that down for energy, just like sugars. It's used for cushioning on our bodies. We have cushioning. We have fat. Well, there's a layer of fat right below your skin called subcutaneous fat, and there's fat that fills up spaces in between or among internal organs. For some, in some cases, it's protecting the organs, cushioning. Thermal insulation that keeps us warm. Um, um, I don't have much, so I usually wearing more clothes than other people because I get cold easily if I'm not moving around. I just cold. Cell membranes. We'll see in the next chapter that every cell is covered by a cell membrane called the plasma membrane, and that membrane is made up of a type of lipid called phospholipid. It's a fat-like material. Waterproofing. Many organisms have lipids. These lipids for waterproofing, like including humans. We have this oily stuff called sebum, produced by our sebaceous glands in our skin that helps to waterproof our skin. Many plants have a waxy coating on their surface to prevent water loss, and that's a lipid. Some hormones are lipid molecules, steroids. So steroid is a type of lipid, and some hormones are steroids. Other hormones are proteins. So fast oils, lipids, steroids, waxes. So fats. This word triglyceride means a fat molecule. And it's called a triglyceride because it's got this part here on the left. It's called glycerol. This is called the head of the triglyceride molecule, the glycerol part. And then there's these three tails. There's a head with three tails. These tails are called fatty acids. So three tails and a glycerol. It's called a triglyceride molecule. And you've heard of saturated and unsaturated fats. That's on food labels in the nutritional information. So what's that mean, difference between saturated and unsaturated? The word saturated means something has as much as it can hold. So if a sponge is saturated, it can't hold any more water. But if a fat is saturated, it's saturated with, hydrogen atom. So this is a saturated fat here, because you see these each of these tails is a chain of carbons with hydrogens attached. And remember, each carbon can have 4 covalent bonds around it. So look at this carbon. It has this bond to a carbon on the left, another carbon on the right, and then 2 hydrogens. And that's kind of blurry. That's an H2. So that's a total of 4. So these carbons cannot hold any more than 2 hydrogens. So there can be only 4 covalent bonds. This one on the end is CH3. It holds 3 hydrogens because it's bonded to only 1 carbon on the left, not one on the right. So all of these carbons have as many hydrogens as they can hold. So we say that's a saturated fat. These fatty acid tails are all saturated. But this is just showing one of these fatty acid tails. So this would be a fatty acid saturated. This is unsaturated because this double bond here. This carbons can be single bonded to each other or double bonded. So this single bond sharing 1 pair of electrons, double bond sharing 2 pairs of electrons. But if there's a double bond, that counts as 2 covalent bonds. So this carbon That's not H2, that's just H there. Because there's one bond, 2, 3, there's only one left. So there could be only one hydrogen on that carbon. If that was a single bond, it could hold 2, and therefore this carbon does not have as many hydrogens as it could have. It could have 2 if that was a single covalent bond between the two carbons. So we say this carbon is unsaturated. This carbon, the other one, is also unsaturated. So that's called an unsaturation on that fatty acid. And so if there was only one of these, like if one of these tails had a double bond in just one place, we could say that's a monounsaturated fat. Probably seen that on food labels. Just in only one place where there's a double bond. If there's a bunch of double bonds, lots of unsaturated carbons, we call that a polyunsaturated fat. Poly meaning many. So which type is considered healthier? Saturated or unsaturated? Anybody know? Yeah, unsaturated. Saturated fats are mostly animal fats like lard and butter. Unsaturated fats are mostly plant oils, olive oil, corn oil, peanut oil. What's the difference? One is more solid at room temperature and the other is more liquid. Which would you rather have in your arteries? Something that's solid or something that's liquid? And why the unsaturated ones are more liquid is that you notice there's a double bond here, but there's also an obvious bend in this tail. These are all, they're zigzags, but they're straight zigzags. This one has a sharp bend. If these are all straight like this, and those triglyceride molecules can pack together tightly in that lipid, and so that's why they're more solid at room temperature. But if there's a bunch of bends, peaks in these, they don't pack together very well, so they're more liquid during room temperature. So the saturated fats, they're the ones that tend to build up in your arteries over time. So your arteries, blood vessels, are supposed to have all this nice hollow space for your blood to flow through, but if you eat a lot of saturated fats and cholesterol, these saturated fats start to build up, and there's a little bit in there, but then after years and years of eating cheeseburgers and pizza every day, that just builds up with plaque until the blood can just trickle through there. And if this happens to your coronary arteries in your heart, these coronary arteries deliver blood to the heart muscle itself, you have a heart attack eventually, because eventually there's no blood getting to part of the heart, and that part of the heart will die. That's what a heart attack is. Part of the heart muscle dies, and if you survive that, your heart, that'll be scar tissue. That part of the blood, that part of the heart, it's not muscle that contracts like it's supposed to, so that heart will never be the same after that. If it happens to a blood vessel going to your brain, you'd have a stroke. Stroke, which is an interruption to the blood flow to the brain. Steroids all steroid molecules have the 4 ring-shaped structures of carbon atoms with other stuff attached. But cholesterol is a steroid, and some hormones are steroids. These are phospholipids that cell membranes are made out of. It's kind of like a triglyceride. It has a glycerol and 2 fatty acid tails, but instead of a third fatty acetyl, it has this called phosphate. It's a little molecule with phosphorus and oxygen that many organic compounds have phosphates on them.
Sir, hey, Stephen, I'm sorry. I have class here for 1 minute.
I'm sorry.
It's okay.
I went over. Sorry. Yeah, okay, let's go. See ya.